If you take out your highlighter, you can highlight quadratic function, and this one right here is the most common one, y equals x squared. Now how would you graph that, or how would you come up with those equations? Well, the most common way when you don't know what a graph is supposed to look like is you make a table of values. What would happen if you plugged in 0 for x? You get 0 times 0 and it would equal 0 for y. So this graph has the point 0, 0. Right? This is the equation of y equals x squared. What happens when you plug in 1? 1 times 1 is also 1. So you would have this point right here, 1, 1. But once you plug in 2, 2 squared is 4, and 3 squared is 9. So we get 2, 4, 3, 9, and numbers get bigger and bigger faster. If you graphed every single value possible, you get this U-shaped graph, which we call a parabola. And it just keeps getting steeper and steeper, and it rounds out like this. And it's symmetrical because if I plugged in -3, what's -3 times -3? It's also +9. So we can get an idea what the shape of a parabola is by plotting some points. Any equation that has an x squared in it is called a quadratic function if the x squared is the highest form. So if we highlight this, this is the general form of the equation, ax squared plus bx plus c, which if you made that equal to 0, that's where our quadratic formula comes in. But now we're looking at graphing all the points. What we did in chapter 3 was just tried to find the points where the x values made it equal to 0. Some characteristics and some important definitions. So I've already talked about it. We call this curve a parabola. Some important points on the parabola. The very bottom or the very top is called the vertex. Sometimes it's a minimum. Sometimes it's a maximum. And on these graphs there should be arrowheads showing that this continues forever. Parabolas are always symmetrical, and so a vertical line that splits it completely in half is called the axis of symmetry. And the axis of symmetry will always go through the vertex. Something else to highlight, so if we look at these graphs that are at the bottom of your page there, we say that a graph where the arrowheads go down opens down, and a graph where the arrowheads go up, we say that that graph opens up. So when it opens up, your vertex is a minimum point. When it opens down, your vertex is a maximum point. And both of those have axes of symmetry. We're going to be asked to describe the domain and range of our parabolas. The domain are your x values. So since a parabola goes up forever and goes to the right forever and to the left forever, there's no value of x that's impossible. We say the domain is everything, and we write it as x belongs to an element of the real numbers. The range, though, your y values, is going to depend on the vertex. So for example, if this vertex right here, if I make up a number and say it looks like it's at 3, 1, and it goes up forever, then I would say the range is y is bigger than or equal to 1. because 1 is the smallest value and it goes up forever. If I looked at this one, and it looks like here, if I make up a value, my vertex is at 3, negative 2. Then my range would be that y values are less than or equal to negative 2. So those are some examples of how the range would change. Yes? Yeah. All right, so let's do our first example. So we have the graph of y equals 2x squared plus 4x minus 6. We want to know what that looks like. So we're going to get a sense by plugging in values for x. We're going to get those values and label them on our graph. Now when you do a table of values, and a table of values is a graphing technique that you learned first in grade 9 and revisited in grade 10. It's always a starting technique for graphing. It's usually the slowest technique for graphing because it takes time to plug numbers in. So you can choose any value for x that you would like to start with. Usually I like to start with numbers that are easy to plug in, like 0. If I plug in 0, I'm going to get 2 times 0 squared plus 4 times 0 minus 6. Mental math, that's going to tell me that's 0, negative 6. Right? Because if I plug in 0 for x, y is equal to negative 6. So I can plot that point on my graph. 1, 2, 3, 4, 5, 6. I have the point 0, negative 6. Now obviously 1 point isn't enough to get a good sense of what this graph is going to look like. So we'll plug in some other points. What happens if you plug in 1? So that means on my graph, on my equation, instead of 0, I'd plug in 1. What does that equal to? 0. Good. So then we have the point 1, 0. Our goal is to plug in points until we find something symmetrical. So we could plug in 2 next if you'd like. Go to my eraser, erase out the 1s. What happens when I plug in 2? What do I get? 10. So I have 2, 10. Does it seem like it's going to just keep getting bigger and bigger and bigger if I keep putting in larger numbers for x? So now I might want to find out, well, what happens if I go in the other direction? Because we want this to make a parabola shape. But right now it looks like if I plug in 3, I'm going to get an even bigger number and a bigger number if I plug in 4. So let's see on our table of values what happens if we start going in the other direction. Plug in negative 1. So now I'll go back to my equation here and I'll say, what happens when I plug in negative 1? Well, negative 1 squared would be positive 1 times 2. Plus 4 times a negative 1 minus 6 will be negative 8. Is that right? And if I plug in negative 2, I'm hopeful right now that -2 will give me my first point that is symmetrical. So if I plug in -2, -2 squared is 4. 4 times 2 is 8. Minus 8 will be 0. Minus 6 will be -6. Oops. I'm going to circle those 2 points right now to say we've found some symmetry. That I've got -6 when I have -2, and I have -6 when I have 0. Because parabolas are symmetrical, that means if I plug in -3, I'm going to get 0. And if I plug in -4, which is one more this way, well, one more this way went all the way up there, I can tell right now that I'm going to have -4, 10. And my picture of my parabola, if I join the dots, looks like that. And from here, we can now determine everything that's on this graph. So starting off with the intercepts. We'll do our x-intercepts first. X-intercepts are where your graph crosses the x-axis. So where does our graph cross the x-axis? At -3 and +1. Our y-intercept is where our graph crosses the y-axis. Can you see that it crosses the y-axis at -6? What are the coordinates of our vertex? Whenever you find symmetry, so that's why these 2 points were really important, your axis of symmetry has to be right between them. So the fact that I found -2, -6, and 0, -6, I know that my axis of symmetry has to go right between them. So my axis of symmetry, which we have to label later anyways, can be labeled by the equation of the vertical line. And you did vertical lines last year in grade 10. I'm not sure if you remember how you labeled them, but they're labeled as x equals because every single point on that line has an x coordinate of -1. And our vertex will be on the axis of symmetry, so we know that our vertex is at -1, -8. Our equation of an axis of symmetry is x equals -1. That's that dotted red line. We always draw our axis of symmetry with a dotted line because it's not actually part of the graph, but it's just there to help us see some of the patterns of the graph. So the axis of symmetry helps us see that it's symmetrical on either side. The domain of the function, this is an easy one for parabolas because the domain will always be everything. The range of the function, that's describing the y values. Well, the smallest y value is -8, so our y values are everything bigger than or equal to -8. All right, questions for practice are 4, 5, and 7.